Okay, we're live. All right. So, Hess's law. Okay. Remember, once more for the people in the back, the path doesn't matter, only the beginning and the end, because we're dealing with a state function. So, say we have some reaction. Our reactants over here, our products over here. We want to measure the change in enthalpy. But for some reason, that reaction is not conducive to measuring that particular change in enthalpy. Well, if we can set up some series of reactions that will get us from A to L, then that'll work just fine. A to B to C to D to E. It doesn't matter what path you take. Normally, it's not, 12 steps. Yeah, 12. But 12 would work just as well. Okay. So you have the enthalpy going A to B, and the enthalpy change going to the C, then the enthalpy change going to D, and then, and so on. They just add together, and that'll do it. Okay? So, for example, nitrogen plus oxygen makes 2 nitric oxide with an enthalpy change of 182.38. Then, 2 nitric oxides will combine with an oxygen molecule to make 2 nitrogen dioxides with an enthalpy change of 82.183. What is the enthalpy change for nitrogen combining with 2 oxygens to make 2 nitrogen dioxides? Okay. So, Hess's law operates kind of like redox reactions in that anything that shows up on both sides of the reaction will cancel out. Okay. All right. So, here we have nitrogen plus oxygen yields 2 nitric oxides. Then 2 nitric oxides plus 1 oxygen yields 2 nitrogen dioxides. So this is a really simple problem because all we have to do to get what we want is add the 2 reactions together. Okay. So the nitric oxides appear on both sides, reactants and products, so they cancel out. There's 2 of each, so they cancel out entirely. Nitrogen doesn't have any nitrogen on the other side, oxygen doesn't have anything on the other side, and nitrogen dioxide doesn't have anything on the other side. However, there are 2 oxygens on the reactant side, so they're going to add together. Okay. So you add those together and you get nitrogen plus 2 oxygen yields 2 nitrogen dioxide. And if I take this away, you'll see that that is exactly what we were looking for. Okay. So these 2 reactions, just as they are, you add them together, they add up to this reaction down here, which means so do their enthalpies. So delta H for this guy is equal to 182.38 kilojoules. The second one is 82.183. So when we add those together, we get the enthalpy change we're looking for. The one is 5, 4, 6, 2. 264.56 kilojoules. Okay. So that is a Hess's law problem. Really simple, really straightforward. Obviously, they can get a little bit more complicated than that. So, in this one, we're looking at 2 reactions. We're trying to get to a third. If you combust methanol with oxygen, you'll get carbon dioxide and water. And when you do that, you have a delta H of negative 1452 kilojoules. If you combust methane, you get carbon dioxide and carbon dioxide and water. And the enthalpy change for that is negative 890.8 kilojoules. Now, this is the reaction down here that we're trying to get to. Combining methane with oxygen to produce methanol. So, with the Hess's law problem, you have to be prepared to rearrange the reactions that you're given in order to get to the final one you're looking for. For example, here we have 2 methanol, and we have 2 methanol down here, but here methanol's on the reactant side, we need it on the product side. So we're going to have to flip this reaction around. So when we do that, we'll flip the sign on the enthalpy change. And on this one, we see that we have methane on the reactant side. We have methane on the reactant side here, but there are two of them. We only have one up here. So we'll have to double this reaction. And when we double the reaction, we'll double the enthalpy. So that's how Hess's law problems work. Whatever you do to the reaction, you also do to the enthalpy. So you flip the reaction, you flip the sign. You multiply the reaction, you multiply the sign, or multiply the enthalpy. And if you multiply by 2, you're going to double the enthalpy. If you multiply by 1/2, you'll 1/2 the enthalpy. Okay? So let's write this out. So we had our methanol on the left, we need it on the right, so I'm going to flip the reaction. So 2CO2 plus 4H2O yields 2 methanol plus 3 oxygen, and the enthalpy change for that is now positive 1452. The other one, we're doubling the reaction, so 2CH4 plus 4 oxygen yields 2 CO2 plus 4 H2O. And now our enthalpy has doubled, so it's going to be negative 1681.6. Okay, so let's go ahead and compare those two reactions. So I took the methanol reaction and I flipped it around. So now the products are on the reactant side, the reactants are on the product side, and that flipped the sign on the enthalpy change. So it went from negative to positive. For this one, I just doubled all the coefficients, which doubled the Hujima thing. So we now add these two things together. I recommend when you're doing these, focus on the things you know will end up in the final reaction, and you know where they'll end up. Don't worry too much about trying to balance the oxygen because it's on multiple sides. Don't try to worry about canceling out the CO2 and the H2O. If this thing works, if you can add these two reactions together, then everything will work out. So 2CO2 cancels out 2CO2. 4H2O cancels out 4H2O. Now we have 4 oxygen down here and 3 oxygen up here. So just like the redox reaction, those 3 go away, then 4 minus 3, we're left with 1. Okay. So now we add our two reactions together. 2CH4 plus 1 oxygen yields 2 methanol. Technically, I should be writing the subscripts, but that's annoying. So the enthalpy change, all we have to do is add these two numbers together. It's going to be a negative 229.6. Yeah, but that'll have to round, equals negative 230 dot kilojoules. And this is our final answer. Because, don't forget sig figs. All right. So once you've manipulated your reactions, flipped them around, multiplied them, and so on, all you have to do is add those numbers. Okay. So here is another example. Carbon dioxide and water make propane and oxygen. Water can be split to make hydrogen and oxygen, and then propane can be broken apart to make graphite and hydrogen. So what is the enthalpy change if you combine graphite and oxygen to make CO2? All right, that one is a little bit more weird. Okay, we have carbon in just the one reaction. We have carbon dioxide only present in one reaction. But we have oxygen present in multiple reactions, we have hydrogen present in multiple reactions, we have water present in multiple reactions, and we have propane present in multiple reactions. So here's how I'm going to tackle this. I'm going to get carbon dioxide where it needs to be. It needs to be on the product side. I'm going to get carbon where it needs to be, over on the reactant side. And I'm going to get them in the proper numbers. Then I'm going to use this middle reaction to go ahead and cancel everything out. So we need, first up, we need carbon dioxide on the right, and we only need one of it. We need carbon on the left, and we only need one of that. So what I'm going to do is I'm going to flip both of these reactions, and I'm going to divide by 3. Okay. So we're going to have 1/3 propane, hey bro, plus 5/3 oxygen yields CO2 plus 4/3 H2O. That's going to give us an enthalpy change of 1776 divided by 3 is 592. All right. Then the third reaction, we flip that and we divide that one by 3 because we need 1 carbon on the left. So carbon plus 4/3 hydrogen yields 1/3 propane. And now we can already see that our propane is going to cancel. Thumbs up. Now we're going to need to use this middle reaction to get rid of the water in the first reaction and the hydrogen in the third reaction. So what we see is we have 4/3 hydrogen and 4/3 water. That's a good sign. Oh, I forgot the delta H. Delta H, we're also dividing this one by 3, so 83 divided by 3 is going to be 27 point, let's see, 2, 23, 7. Okay. Now, so we're going to take this middle reaction and we're going to multiply by 4/3 because we need 4/3 water on the left, we need 4/3 hydrogen on the right. So when we multiply this by 4/3, we're going to get 4/3 water breaking up into 4/3 hydrogen plus 2/3 oxygen. Okay. And our enthalpy change, oh, this is going to be more annoying. So divide by 3, that's going to be 76. Multiply by 4, 76 times 4 is 280. Plus 24 is 304. Okay. So let's go ahead, cancel everything out. Our 1/3 propane will cancel out. 4/3 hydrogen cancels out. 4/3 water cancels out. Now we have 5/3 oxygen versus 2/3 oxygen. The 2/3 will completely cancel, then 5/3 minus 2/3 leaves us with 1. So our final reaction is carbon plus oxygen yields CO2. Everything worked out just fine. This one is a kind of nasty one because you have to multiply by fractions, but that's perfectly fine. It worked out in the end. You just got to be okay at working with fractions. Okay? So now we add together our 3 numbers here. Do I have the signs correct? No, I don't, because I flipped this one and I flipped this one. So those are both negative. So, is that right? Yes, good. Okay, so got to be careful about those negative signs. Okay, so 592 plus 28 gives us 0, 1, 3, carry the 1, 630, minus 304, 623. So our delta H is negative 326 kilojoules. Okay, be careful of those signs. They will screw you up. Flip the reaction, you flip the sign. The problem there was that I was flipping the reaction and dividing, so I forgot to do one of them, and that was bad. All right. So those are Hess's law problems. Practice, 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 practice. You'll definitely have to do at least one of these on the test. They are a super duper important kind of thing. They allow us to do a lot of chemistry because a lot of the time the reaction we want to study hasn't been recorded, but other reactions have, and we can work with that. In fact, a lot of reactions have been studied so well that a lot of the time we don't need to do this really big, complicated thing. But they will still ask you to do this really big, complicated thing on the test. So practice. Google practice Hess's law problems, right? And you will get a ton of these, okay? Always Google is your friend there. All right, that is it for this set of slides. I'll be back in a few minutes to talk about the enthalpy of formation. See you in a few.